Hello, myself Kaustubh Dwivedi, and today we are going to discuss how to calculate the number of bound states in a finite potential well. And when I say in the previous video we discussed the barrier potential, now we are going to do the potential well. A question related to potential well we have solved in the first video, which was the infinite potential well. That is the most basic solution in quantum mechanics. Today we are going to do it the finite potential well, where the height of the well is not at infinity, which means that the boundaries of those two wells, in the first case it was infinite potential, in this time it is not infinite, it is finite. Now the later was also boundary condition, the later was also solved using boundary conditions, and this is also going to be solved using boundary conditions. And so let's start. I don't think I have to say a lot. Okay, so finite potential well. It's very simple. As usual, how we solve this kind of questions. Now look, these are two potential steps. Now these steps go to infinity in the distance. These steps go to infinity in distance, but the height of these steps, where the potential V is not at infinity, V is at V0. So let's say this is V0, and we have to take a condition where, okay, this is a V0, this is a X, and this is, let's say, minus A by 2, this is plus A by 2. Now, taking the distance to be from minus A by 2 to plus A by 2, we are making sure that this system, the potential becomes, the system becomes finite, and also the distance becomes finite, and the potential is symmetric in nature. From minus A by 2 plus A by 2, it means that V of minus X is equal to V of plus X. It means the potential is what? It means the potential is symmetric in nature. And if we have a symmetric potential, we can find two kinds of wave function. One is the odd wave function, another one is a even wave function. So we have to remember that this is your region 1, this is your region 2, this is your region 3. In region 2, you must have odd function and even function both, because both are possible. If the potential is symmetric, we know that the psi can have both odd sign and also can have even sign. That is kind of a property of symmetric potentials. Now, okay. Now, second case is that we have to take a condition of energy, and the energy has to be less than V0 for the case to have a bound state. Because if we take energy greater than V0, we won't get the bound states. The necessary condition for the bound state is that the energy of the wave has to be less than the potential. Got it? So let's take the energy E. E is less than V0. So the condition is energy is less than V0. Now here it's a very simple thing to do. This is region 1, this is region 3. Region 1 and region 3 will give us exactly the same value of our propagation vector. So let's calculate it. In this region 1, E less than V naught in the region 1, our Schrödinger equation will look like this will be our Schrödinger equation. Now when you solve it, it goes like now as we are solving it here, I think everybody can understand this how this step happened. But this sign convention doesn't suit our purpose, because this E minus V is coming out to be less than 0. So we have to change it, as we do in every problem like this. We have to change it as V naught minus E of psi 1. And as we solved already this kind of question, we have to assume this to be our new I hope everyone understands how this happens. And for those who don't know, we have assumed nu to be root over of 2m V naught minus E by h bar square. This is the first step. This is the wave function in region 1. Now look, when we solve, this is the part where our equation will become psi 1 equal to a e to the power nu x plus b e to the power minus nu x. I hope everyone understands this. Now look what we are doing here. If you see, the region 1 is at a point when x is less than 0. So when you put x is less than 0 here in this equation, you can see psi 1 for x less than 0. You can see this term diverges when x tends to infinity. This term diverges at x tends to infinity. Because if you put x minus x in this point, this whole minus nu x will become plus nu x, and x tends to infinity tends to infinity. So this condition doesn't suit our purpose. So what we will do? We will for this condition, b e to the power minus nu x diverges. That implies we need to use b equal to 0 for the suitable solutions. Now take b equal to 0, and that will mostly solve our cases. Now psi 1 becomes your a e to the power nu x. This is 1. And look at it. The way we solved the region 1, the exact same way we will find out our region 3. Yes? Now let's do that. Region 3. Now region 3 will give us what? Del square psi 3 by del x square minus nu square psi 3 equal to 0. Now we will have psi3 equal to two different functions, let's say f e to the power nu x plus g e to the power minus nu x. Okay, now here x was less than 0, that's why this term was diverging. Now here what is the condition? X is greater than 0, so which one will diverge? This one will diverge. So f e to the power nu x diverges at x tends to infinity. So we have to take f equal to 0. We need to use f equal to 0 for the suitable results that we need. Okay. Now what is our psi3? Psi3 becomes g e to the power minus nu x. Alright. Okay, psi1 is done, psi3 is done. What is left? Region 2. Look, region 2 is technically very simple. Region 2, there is nothing to really think about. In the region 2, you don't have to think about anything. But what happens is that when we solve this potential well, the problems related to potential well, we have both odd solutions and even solutions. To accommodate that fact, we use sine function and cosine function to solve it. Earlier, we used to solve it using exponentials. Here we use sine and cosine function, and I think that's what solves it completely. Now in this region, the potential is 0, so our k1 is going to be root over of 2 m e by h bar square, and psi2 is basically c sine k1x plus d cos k1x. And I think that solves the condition very well. This solves the condition very well. Now, if you need the sine part, then you will get an odd solution. If you use the cos part, you will get an even solution. That's basically it. Now what we need to do now in these kind of questions? What we do? We use boundary conditions, and here we will exactly do the same thing. Nothing going to change. Let's do the boundary conditions. Okay, so first we have to do for odd function, then we have to do for even. First we will do for the odd. Now psi odd is equal to what? First we will have a e to the power nu x, a e to the power nu x. This happens from minus a by 2 to 0. It becomes from x less than minus a by 2. We'll have for the odd we'll have c sine k1x from minus a by 2 less than equal to x a by 2. From this region, this will be c, and from the region beyond it, it will have g e to the power minus nu x, which is for x greater than a by 2. This is your wave function for the odd part. Now here let's take the boundary conditions, and here you don't have to use the both boundary condition. You can do it with one boundary condition also. Let's see how it happens. So we have to use this first condition is psi 1 at minus a by 2 is equal to psi 2 at minus a by 2. That will lead us to a e to the power minus nu a by 2 equal to c sine minus k1 a by 2. Now sine minus x is equal to minus sine x. So a e to the power minus by 2 is equal to minus c sine k1 a by 2. I hope you got it. Now let's take the derivative of it. Psi 1 dash minus a by 2 has to be equal with psi 2 dash minus a by 2. Now when you take derivative of it, it becomes minus nu a e to the power minus nu a by 2 plus c. Now okay, in this case you have to first use c k1. It becomes cos now. It becomes cos. Instead of this k1 you have to use instead of k1x you have to use minus k1 a by 2, but in case of cos, minus cos x is equal to cos x. So you can write it exactly like this. Nothing changes. Okay, very good. So now look at these two equations, this equation and this equation. If you divide these two, you will have minus 1 by nu is equal to minus wait a minute. So when you use this part, yeah, it's okay. So when you use minus nu, okay, wait a minute. This is coming. Okay, so I made a mistake here. I have made a mistake here. I have forgotten this part. Sorry. So this will be the case. I made a mistake. It's funny. I make these kind of mistakes. I don't know why. So this becomes cot k1 a by 2. This cot k1 a by 2 into is equal to minus nu by k1. Now we can do this like this: k1 a by 2 into cot k1 a by 2 equal to minus nu a by 2. If I write this function in this way, nothing will change. Now let's assume this to be your eta, and not eta, it's like a e. I don't remember what the sign is of cot e is equal to minus, this is eta, this is for asymmetric solution, and or for the odd solution. I hope you get it. This is the asymmetric solution and for the odd solution. Similarly, when you use the boundary condition for the even wave function, you will get another condition which is basically this. You will get E tan E, which is equal to eta. How will you get it? Instead of C k1x, if you use D cos k1x, that will be a symmetric solution, and you will find this equation. These two are now your this is the solution for symmetric even. Now these two are your required system. These two are your required system, and then you have to study how you can find bound state using these two equations. Now, before we go there, I have to draw a diagram of eta and E. So I have to remove this part. I have to remove this part, and then there I will use the equation or the graph, basically the graph which we need. Now look at it. This is a plot. All right, this is 0. Let's say this is our E. This is our eta. Okay. Now this is your 0. This is pi by 2. This is pi. This is 3 pi by 2. This is 2 pi. This is 5 pi by 2. And this is your 3 pi. This is how the system goes, the theta goes, or the k value goes. The k value k1, k2, it goes on. Okay, so people, you might think why the k1 into a is coming out with this. So if you have studied condensed matter physics, you would know that the k1a is basically gives us the value in radians. So, and look, we have two equations. One is for asymmetric where eta is a function of minus cot E. Eta is a function of minus cot E. In another case, eta is a function of plus tan E. Now we know tan theta goes to 0 at x equal to 0, and tan theta goes to tan theta goes to 0 at x equal to 0, and tan theta goes to infinity at x equal to pi by 2, or theta equal to pi by 2. So at pi by 2, tan theta will be what? Will be infinity. So now the equation of tan okay, wait a minute, I have to draw the shaded line for me to keep the limits safe. Okay, so now tan E will start from here. It will not touch here. It will go to infinity. But the cos part should come here, from here like this. But here the cos is what we have, minus cos. So the cos part will be inverted. So this will be your cos. Again, this will be your tan, and this will be your cot. This will be your tan, this will be your cot. Remember, it should not touch. It should not touch. I mean, the theta will not reach infinity exactly. As it goes close to the pi by 2, that will touch the infinity, but it will reach infinity at a very high stage. It will not touch just like this. I hope you understand what I'm saying. Now if you do this, look at this. If you take this equation, very simply, you take the equations. Let's say we have E equal to K1 A by 2, and eta is equal to nu A by 2. Okay. From this, we can find K1 to be 2 E by A and nu, which will be 2 nu 2 eta by A. When you take square of it, K1 square plus nu square, what will we get? We will get 4 by A square E square plus eta square. Alright. Now what will this value give us? This value will give us, look very carefully, this value is nothing but square of this plus square of this. What will this will give us? This will give us 2m v naught by h bar square. Now if we use this, then basically our E square plus eta square becomes m v naught by 2 h bar square into a square. Got it? This term, we can assume this term to be your r square. Now look at this. Is it not an equation of x square plus y square equal to r square? Yes, it is. Now what we can do? We can draw a parts of circles here. We can draw parts of circles here. Yes or no? Now once the radius increases, we can remove this part, not needed, and also this part, extra. Okay. Now these kind of circles we can draw. Now when we are drawing this kind of circles, we also should know that this circle is crossing the equation at one point. This circle of radius pi by 2 to pi is crossing the circle at 2 points. This at pi to 3 pi by 2 is crossing the circle at 3 points. These points, these cross sections, or I would say this point of intersections, are basically your number of bound states. Now in the very first system, you can calculate this very easily, that the first system from 0 to pi by 2 is going to give you an even function. This is an even. But now here you will have one even and one odd. This is odd. This is your even. In the third case, you have to one even, two even, but one odd. This is how you calculate the number of bound states. Now in this entire scenario, we can do some kind of math, which we can tell you that, okay, the number of bound state depends on what? Only on the radius. Now the radius of that depends on potential and the length, the width. Two cases. The number of bound state in a system can be calculated by the depth of potential and the width of the box, or width of the well. So for example, let's say if we say r square is equal to m v naught a square by 2 h bar square, that implies v naught is equal to 2 h bar square by m a square into r square. Yes. Now look at it. For one bound state, for one bound state, what will be the value? From one bound state, R starts from 0 and ends at pi by 2. So potential has to be 0 less than V naught less than what? Instead of R, you have to use pi square by 4. That will give us h bar square pi square by 2 ma square. This is the value of V naught, which requires to be in this region to give us one bound state, and that one bound state has to be our even bound state. Okay. Now similarly, we can, if the question comes related to this, we can see the potential or see the width and then calculate. Let's say the question comes with two different potentials. So we have to rewrite the boundary condition again, and we have to find out. I think that's what we do in this kind of questions. This question looks a bit messy, and this question is messy. Technically, what we do in this question is that we only study this part. We don't do the derivation, because only the important parts are this. Now there is one case which I want to explain. That case is, look, this is a very important case, but this is not important for the derivation, but it's important to understand how we approach a question. Look, if in the case where V naught tends to infinity, now if the V naught tends to infinity, this exact problem becomes what? The infinite potential well. V naught tends to infinity. Now when we use V naught tends to infinity, what we do basically? For V naught tends to infinity, it means that R will also go to infinity. R will also go to infinity. Yes. Now these two conditions will be satisfied when our tan Ka or tan E tends to infinity and cot E tends to infinity. Now tan E tends to infinity, we can find it where? Where does tan goes to infinity? At pi by 2, or we can write it as n pi by 2. Okay. Or for n pi by 2, where n equal to 1, 3, 5, 7, ... Yes. Now where cot E goes to infinity? Cot E goes to infinity as 0, pi, 2 pi, and that can be written as this. That's also equal to n pi by 2. E to be n pi by 2, where the value is 2, 4, 6, 8, 0, and we don't take 0 to be a radius. Now look, this is the solution, this is one solution, this is second solution. Both of it, if we combine, what will you get? We will get eta to be n pi by 2, where n equal to 1, 2, 3, ... Alright. Now instead of eta, we can write it as k a by 2 is equal to k1 a by 2 equal to n pi by 2. 2 pi goes, k1a equal to n pi, and k1 equal to what? N pi by a. Now what is the condition of energy? H bar square by 2m into k square. K square is n square pi square divided by a square. Isn't it our energy solution? Isn't it our energy solution for infinite potential well? This is the same thing can be derived from this equation also, using this condition. I hope you understand. I know this problem is a messy one. So I didn't want to solve it because I wanted to do it first by doing some problems on this by using this formula. But let's say I solved it. I'll do problems. I'll discuss problems. Yeah, I will discuss some problems. But one thing I'm thinking of is that I will do problems, but I will not explain those problems. It's like I will in the screen you can see the problem, and I will only solve the problem. The sound will be zero. There will be no sound. I'll only go down there in the road and solve the questions. Because if problems are very important, I don't want to waste time while doing questions. So the maximum output a student can get, or my maximum output a student can get while solving problem is that he should not talk, and that is what I do, and that is what I am going to do. So I hope you understand, and I know it's a bit messy. If you have some problems, you can tell me. I'll improve in the next videos. And thank you. Keep watching.